epsilon multiplied by the applied field. Alpha epsilon is usually referred to as the electronic polarizability of the atom. The linear relationship is, however, only valid when we have low-level field excitations, or that is low field excitations, not when E is very large. Any molecule will develop a dipole moment proportional to the applied electric field in the low field case, and therefore we can generally write for the molecule that the dipole moment P is equal to alpha multiplied by the applied field E, where alpha now is a total polarizability, which is the sum of the 4 different polarization mechanisms that we saw before, that is electronic, ionic, orientational, and also space charge. So if we multiply the dipole moment by the number density of the molecules forming the dielectric, we'll get what we call a dipole moment volume density, which is generally referred to as a polarization vector or simply polarization. So polarization may be expressed in the form P equal to the number density of molecules multiplied by the number of, or the dipole moments that we have per molecule, and this is given by N alpha multiplied by the applied field E, and this can generally be expressed as chi epsilon naught, which is the permittivity of free space, multiplied by a factor chi E and multiplied by that electric field that is applied. So epsilon naught chi epsilon is equal to N alpha, and chi epsilon is usually referred to as the electric susceptibility of the material. So in an alternative way, we could always write the induced polarization P as, that is from the previous slide, and we're multiplying that one by, instead of using the applied field, we use the local field at the molecule that we are dealing with. This local field is going to be different from the applied field because the displacement of the centers of mass of the positive and negative charges will develop an induced electric field that opposes the applied field at that particular position. And therefore, this is usually given by N alpha multiplied by a factor G multiplied by the applied field, where we are now saying that G, okay, the alpha is the total molecular polarizability, the N is the molecule number density, and G is the ratio of the local field that is acting on the molecule under consideration in relative to the applied field E. Remember, the local field cannot be measured, but we can measure the applied field. So EI and E are different because of also the surrounding molecules that will be acting, okay, the surrounding dipole moments surrounding the molecule of interest will also affect how EI is going to be. So the flux density, or the electric flux density, usually called the electric displacement, is therefore given by D equal to epsilon multiplied by E, and where epsilon is given by epsilon naught multiplied by the dielectric constant epsilon r and multiplied by the applied field E, from which we can therefore see that the relative permittivity or the dielectric constant may be expressed as epsilon r equal to 1 plus N alpha multiplied by the G factor divided by the permittivity of free space. And this gives us a value of 1 plus chi E, or 1 plus the electric susceptibility. So if the surrounding molecules will act as point sources, therefore they have spherical symmetry, then the molecule for which the local field EI is being evaluated, G has been shown to be given by G equal to epsilon r plus 2 and divided by 3. This is from geometry consideration, where you are having a material, you remove one molecule, the molecule you are dealing with, get it out, and therefore you treat it as a cavity and see what happens between the two. And therefore, if we do this, we can write that epsilon r minus 1 over epsilon r plus 2 is equal to N alpha by twice alpha naught, which is equal to alpha by 3 epsilon naught, and multiplied by the Avogadro's number divided by the molecular molecular mass of the particle, and multiplied by the its mass density, the mass density of the material we are dealing with. So this is given down below, and rho is the mass density, while that is the Avogadro's number. You can recall this from physical electronics, where we were dealing with the bonding or the crystals, so to speak. This expression is usually called the Clausius-Mossotti equation. But if we were to use the value of alpha as a function of frequency, the equation will be referred to as the Debye's equation. So this expression is most accurate when you are dealing with gaseous dielectric rather than solid. In general, the total molecular polarizability is given by the electronic polarizability plus the ionic polarizability and the orientation or dipole orientation polarizability plus the space charge polarizability. Okay, and therefore, if we were to, we can always look at a polarized dipole in terms of equivalent volume on surface densities. So if we apply an electric field to a dielectric, okay, we cause the formation of the electric dipoles within that material, and this then establish an electric field of their own. So the polarization vector or dipole moment of a volume density will be defined as P equal to the limit as we make the volume we are considering tend to 0. I think I should put a 0 here, is given by the first molecule to the nth molecule multiplied by the dipole moment per molecule. So n is the number density of the molecules, and pi is the dipole moment of the ith molecule. Remember, delta v prime, although we say it's going to tend to 0, it cannot be 0 because we know that we are dealing with particles that have finite volume. So all we are saying is that once we do this, we make the polarization vector or the volume density of dipoles to be a smoothed point function. That is a continuous function in space, but it's a smoothed one, because we know that since each molecule occupies finite space, it will be some kind of discrete, but we are now trying to pretend that this can be written as a continuous function. So the dipole moment of an elemental volume of dielectric dV prime is then given by the d multiplied by p equal to p multiplied by dV prime, because we know this is dipole moment per unit volume, and that is the total dipole moments. So this therefore establishes an electrostatic potential d phi that will be given by d phi equal to the polarization density, okay, or the polarization dot the unit vector, where this value is the unit vector in the direction of the observation point, and that is, we are assuming that that of course acts as a point source, and therefore we just use the surface density of a sphere. Someone has their microphone on. Could you please mute it? So R is given by the position vector of the observation point, and okay, relative to the position vector of the source or the volume of the element of volume dV prime. And therefore, the unit vector is of course given by that expression there. Okay, will be the unit vector in the direction of R minus R prime. Now, when we do this, we are of course assuming that the field point is sufficiently far away from dV, such that dV, even if it occupies finite volume, it now looks like a point source from where we are looking at it. So the total potential due to the dielectric polarization is therefore going to be given by, excuse me. Any issues? So we are going to get that from the equations you already met in third year with electrostatics. This is what you would get for a point source or a point charge. This would be the potential, okay, that will be established. So in a Cartesian coordinate system, we have that R will be expressed as the position x of the field point relative to the position x prime of the source or the point source plus the usual equations there. And therefore, if we were to take the gradient of 1 by r with respect to the coordinates of the source point, that is the coordinates of the source, where now we are differentiating not with respect to x, but with respect to x prime, y prime, and z prime, then we can see that this equation, if we were to do that, we'll get that this is going to give us the gradient or the del operator at the field point multiplied by 1 by r. And this will give us a value of r prime over r squared. And we can therefore express the potential in the form 1 over 4 pi epsilon integral over the volume surrounding the material, that is the dielectric, multiplied by P dot the gradient of 1 over R, okay, dV prime. So from vector identity, we know that the divergence of a vector that is multiplied by a scalar function psi is going to be given by psi multiplied by the divergence of that vector plus that vector dot the inner product, the dot product with the gradient of the scalar function. And therefore, we can express phi in the form 1 over 4 pi epsilon. That equation that is where our function now, the a here is going to be p prime, and our psi prime, psi is just 1 over r, and multiplied by dv minus 1 over 4 pi epsilon integral of v prime, the divergence of p over r and dv. Now, once we have this, we can always use the divergence theorem to try and reduce these equations into surface integrals as well as volume integrals. So the first term will be given as 1 over 4 pi epsilon r, that is p dot n cap ds prime. We should use n prime, n cap prime, because we are dealing with these coordinates of the source, okay, where the n is, of course, the outward unit normal on the ds that is bounding the volume element dv prime. And the last equation, of course, is 1 minus 1 over 4 pi epsilon r multiplied by that. We recall that the potential field for a surface charge of surface charge density rho s per unit area is usually given by phi equal to 1 over 4 pi epsilon integrated over the surface that is surrounding that point source or the charge distribution, and will be given by rho s over r ds prime. For a volume charge distribution rho, okay, coulombs per meters cubed or per unit volume, we saw that the expression we obtained from the electrostatics is given by rho by r and multiplied by d ds. So rho is in units per unit volume, rho s is coulombs per unit area. And therefore, once we look at that, we can therefore recognize from the expression of the polarized dielectric, the potential due to the polarized dielectric, the first term therefore represents the potential field of an equivalent surface charge distribution rho or ps equal to p of the polarization dot the unit vector of the unit vector on the surface. The second term is the potential field of an equivalent volume charge distribution rho P given by the minus of that divergence of the polarization. So rho PS and rho P are then called polarization or bound charge densities. They are not free charges. So the dielectric doesn't have any free charge, but they are charges that are appearing due to the induced dipole moments in the material. And therefore, this means that the polarized dielectric can be replaced in any analysis that we are trying to make, any field problem we are attacking. We can replace the polarized dielectric with an equivalent surface volume and volume polarization or bound charge densities. Okay? And therefore, this means that the potential due to the polarized dielectric may then be expressed as phi equal to 1 over 4 pi epsilon integrated over the surface volume, the bound surface charge densities, plus 1 over 4 pi, the integral of the volume, or the bound volume charge density over the volume of the dielectric. So this result appears to be mathematical, but it always has a physical density, which we can always express as follows. Consider a polarized dipole of that nature, or dielectric of that nature. We can see that inside in the bulk, we have the tail and head of the dipoles will be aligned to each other, and therefore we can expect that there will be total cancellation if we have uniform distribution of the dipoles. But at the surfaces, we have the uncompensated negative, the tail of the dipole, and the positive tail of the dipole as shown. So suppose we consider as an element of surface somewhere where we just cut down the slab, and we have a surface delta S, okay, inside the dielectric. Now, when we apply an external field, the positive and negative charges will be displaced at total distance given by d as a vector, where d is a displacement, and the dot product with the unit vector, where the unit vector, of course, we have that this is when we have the S not oriented normal to the D, the displacement. That is, or we are applying the field not normal to that surface. And therefore, we see that the positive charges will move at distance d dot n by 2 in the direction of the field. The negative charges will move an equal distance against the field. And therefore, the net charge crossing the surface delta S in the direction of the field will be given by the net movement of the positive charges, that is those minus that one. And we get something like Qn multiplied by the d dot n and multiplied by delta S, where delta S is the element of volume we are considering. N, that is the n without the cap, is not the unit vector, that is magnitude. All we are saying is that that is the number density of the charge carriers. So, but if we multiply Qn and multiply that one by the displacement d, is of course equivalent to the dipole moment volume density, which we call the polarization P. And therefore, the delta Q is going to be given by P dot n cap delta S, and the surface bound charge density is hence going to be given by rho PS equal to delta Q by delta S, and we can see that that is going to be given by P dot n. Remember, here it may be confused because we are using, sometimes we are using prime, sometimes we are not using the prime. But as long as there is no ambiguity, we can always drop the primes so that we just get those values as shown there. So this is the correct value of the positive surface charge on the right side of the face of the slab, and this will be numerically equal to that of the negative face, the left-hand face of the dielectric. So the net charge that will be leaving the volume through the bounding surface S of the dielectric due to polarization will therefore be the integral of rho PS over the volume V of the dielectric. And the net charge remaining in V must then be the negative of that integral, or rather that Q is going to be given by minus the surface integral of P dot ns, which is equal to that value there when we use the divergence theorem we will get that kind of value, and we see that that is going to be the bound volume charge density in there. So thus, as long as the divergence of the polarization is not zero, the bulk of a polarized dielectric will appear to be charged. But because the dielectric is initially uncharged, the net charge must always be equal to zero. And this we can verify by writing that total charge is going to be given by the total charge due to the surface distribution of charges plus the charges inside the bulk of the material, and all these must be equal to zero, and we get that value like that. So this may be understood by considering an uniform polarization that will occur in homogeneous dielectric media when we deal with those later. So partial cancellation of the interior charges will produce a volume charge density, and uncancelled charges at the surface of the material will give rise to the surface charge density, and that connects the mathematics to the physical. So the surface charge density in the interior of the dielectric will be zero, while the volume charge density will be given by rho p equal to minus delta with the divergence of p prime. So since the dielectrics contain no free charges, that is, perfect dielectrics will have no free charges, the bound charges may be expressed or represented by the volume charge density, and the Gauss law therefore then applied, and we get that the delta or the divergence of epsilon naught multiplied by E, where this is the free without the dielectric, and then we consider that must be given by the bound volume density, where we are now replacing the dielectric with its equivalent volume charge density, okay, bound charge density due to the polarization. This is Gauss law, because we say that Gauss law says that the integral of the electric displacement around a surface, okay, surrounding or bounding a volume V containing charge will be equal to the net charge enclosed. And this is the net charge that will be enclosed there. That is P rho P. So we can take this to the other side and put them together, and we see that the divergence of epsilon naught E plus the polarization P must be equal to zero. And we define therefore an electric displacement or flux density D to be expressed as epsilon naught E plus P, or the polarization. And hence, for a perfect dielectric without free charges, we have that del, or the divergence of the electric displacement, is going to be equal to zero. In the presence of free charges to a volume density rho, that is, we have rho coulombs per unit volume free charges in our dielectric, that is, our dielectric is lossy, the divergence of D must be equal to the total charge enclosed, and that would be given by rho. This is what we obtained before. Remember that rho now, this one is not the bound charge, but just the free charge carriers in the dielectric. So the electric field theory may be further simplified when we invoke the proportionality between the polarization and the electric field intensity, especially when you are dealing with low-level applied electric fields. And we may therefore write that D is going to be given by epsilon into 1 plus chi E, and multiplied by E, which is equal to epsilon naught epsilon R, multiplied by the applied field of epsilon, just simply the permittivity of the dielectric, and multiplied by the applied field. So 1 plus chi epsilon is interpreted as a relative permittivity epsilon R, and this is a characteristic of the material. So this expression will apply only to the interior of the dielectric, but there is nothing it says about the surface, the boundary conditions on the surface. So if we consider a dielectric medium with a surface charge density rho PS as shown, that is, we have rho PS on this surface, the inside we have the electric field and polarization Pi, and that will be EI, the electric field inside the dielectric. Outside the dielectric, we have that of the electric field will go to that one of the free space or the outside electric field, and that will be the outside polarization. Okay. So in the presence of a surface charge, the boundary conditions then become that the displacement outside the dielectric minus the displacement inside the dielectric must be equal to the surface charge density, okay, or the charge density on the surface of the dielectric. Or in other words, if we write this value, if you look at that, we are going to get epsilon naught multiplied by E. We can see that P0 is going to be 0 if we are dealing with free space outside the dielectric. Okay, that is not another material, a material which is not polarizable. So the outside displacement minus the inside displacement must be equal to 0. And therefore, this says that the displacement outside the material minus the displacement inside the material must be equal to 0. It means that the normal component of the electric displacement is continuous across the boundary on which there are no surface charges. That is, when there are no surface charges, then this equation must always hold. So the equivalent surface charge density will not affect the tangential component of E, and therefore the tangential component of the electric field intensity will be continuous across the boundary, just like we have already proven in the previous lectures. So the permittivity concept allows an easy solution of problems that might be very difficult sometimes to formulate when we use the dipole distribution concept. But the two concepts must be kept separate if we are describing our dielectric through either its permittivity or we are using its dipole charge distribution, that is its equivalent surface and volume charges. So what would be the frequency response of the electric field for the electric materials? The frequency response of a material or the dielectric material will be described by the frequency response of its dielectric constant, or that replaces or that defines its polarization. So polarization of material requires the displacement of particles, each with a finite non-zero mass, especially if we are dealing with a gas, so to speak. So thus, the strength of the polarization will decrease with increasing frequency, because as the applied field changes direction, we expect the polarization direction in the material to flip sides. And since these particles that are carrying the polarization are finite mass, they will require a finite amount of energy to move them around. And therefore, they will not be able to follow the changes in the applied fields if the frequency is high. Okay? That is, the particle inertia will tend to prevent the particle from following the rapid oscillations of the applied field. So for a quantitative understanding of polarization, it's usually sufficient to just consider the electronic polarization, because most of them will follow similar kind of relationships with the applied field. And therefore, once we understand how electronic polarization works, we can always just replace the polarizabilities with the appropriate parameters of the actual mechanism that we are dealing with. So the other types of the polarizations will therefore exhibit similar characteristics, though most times if we have any resonances, the resonances will be less sharp. So for convenience, we regard that the heavy nucleus is fixed in space relative to the surrounding electron charge cloud. And we are assuming that the charge cloud is of spherical symmetry. So we assume a charge cloud has a total charge of minus Q. This is not the electronic charge, but now we are just using Q as a general amount of charge for the electron cloud, not just one electron. And the mass of that charge cloud is going to be given by M. This oscillates in response to the applied alternating current electric field. So when we apply the field, the center of mass of the electron cloud will be displaced from the rest position with respect to the nucleus in response to three forces. One, a force that will be exerted by the externally applied field, which is minus Q multiplied by E, or where E is the applied field. Two, there will be an electroning force trying to bring the displacement back to, or the electron cloud back to its rest position due to the displacement of the positive and negative charges, which introduce or establish a Coulombic attraction. And two, and three, there will be frictional forces if the particle is actually flipping, physically flipping from one, following the applied field. There will be kind of damping effects due to friction or something like that. So we have some damping effects to the charge oscillation. So we assume that the applied field has a harmonic time dependence given by Ex, where we are using a field or a wave that has X polarization given by epsilon naught multiplied by the exponent of j omega t. We are not taking, we are just ignoring any traveling nature of the field, and we are just looking at the time response. So the restoring force will be proportional to the charge displacement x of t, and it will be given by Fr equal to minus S x of t, where S is the stiffness, which is like a spring constant due to the, that is connecting those two values there. Okay, that is it's a proportional, the concept of proportionality between the force and the displacement for the Coulombic attraction. Okay, and the displacement for this to happen, we are assuming that x is small, so and s will be a constant. So the frictional force itself is given by a force that is proportional to the velocity of the particle, and we are giving it a value m, which is the mass of the particle, multiplied by the constant zeta, and multiplied by the velocity of the particle as it's moving. So thus, the equation of motion may be expressed in the form that the mass, that is Newton's second law of motion, which is mass times acceleration plus the frictional force plus the displacement or the restoration force must be equal to the total mass or the total force applied, or the applied force. Here, what we have done is that we have now divided that by m, and therefore we can get that S by m equal to that value there. So this equation is a simple harmonic equation, if we were to look at it, and we can see that with Ex having harmonic time dependence, the displacement can also be expected to have a similar dependence as well. And therefore, we are going to guess a solution for the x of t that has a harmonic time dependence as well. So one possible solution would be a value in phasor form given by x of t equal to x naught multiplied by the exponent of j omega t, and the physical field can then be extracted from this phasor form by just multiplying everything by the exponent of j omega t to get the values. So here we get that this is going to be, the Ex is going to be given by R E or E naught multiplied by the exponent of j omega t, and the displacement as a function of time going to be the real part of x of t. So when we use the solution of x in the equation of motion, then we obtain this value that omega squared minus j omega zeta minus s by m multiplied by x is equal to q by m and multiplied by e. This reminds you of an RLC circuit, okay, which we can see that the square root, this would be a characteristic frequency or the resonance frequency of the RLC circuit. That would be the damping coefficient, okay, for that particular circuit. So we can see that x is going to be given just simply by the minus of q by m Ex over and omega p squared minus omega squared plus j omega zeta, where omega p is just simply the square root of s over m. This you can recall from Hooke's law when you are dealing with springs. And therefore, the displacement x of t is just going to be given by the real part of that equation, which we can see is just going to be q cos phi over that equation, where phi is now the angle or the arctangent, not a tangent. This should be the arctangent of omega zeta by omega squared minus omega p. This is an error there. So the dipole moment, polarizability and polarizations are then going to be expressed as the dipole moment in the x direction is just going to be given by the charge that we are dealing with, multiplied by the displacement, and you can see that that is going to be given by minus q of that squared over that. The polarizability is just the polarization divided by the per unit electric field intensity, and that gives us that equation there, where we are just dividing that by the value of ax. And therefore, the polarization in the x component is going to be given by that polarization, the dipole moment, multiplied by the number of dipole moments per unit volume, n, and we get that equal to that minus multiplied by that value there. So the dielectric displacement is therefore going to be given by what we said is the free space displacement plus that due to polarization. And we see that that becomes that equation, and we can always express that in the following form, where epsilon r is of course going to be given by 1 plus chi e, and we see that 1 minus that value multiplied by that. Okay, so we are going to see the following. We express this in the following form, that the epsilon r, or the dielectric constant, is going to be given by a real part of the dielectric constant minus an imaginary part of the dielectric constant. And this represents the loss in the material. So epsilon r is going to be given by the real part of what we have already defined above, and the epsilon double prime is going to be given by that equation there. I think there's that somewhere is correct. So these expressions are usually referred to or called the dielectric dispersion formulae because of that dependent and linear dependence on frequency. We'll see that they'll have different values for different frequency of applied field. So epsilon r will be associated with dissipation in the dielectric and will lead to the macroscopic effect of non-zero conductivity in the dielectric at any given frequency. So dielectric losses will often be described through the tangent of the phase angle of the relative permittivity as follows. And the tangent of delta L, or the loss angle, is going to be given by epsilon r double prime divided by, that is the imaginary part, divided by the real part. So when we plot that against frequency, the property of the dielectric will change most dramatically around the resonance frequency omega p. Remember, don't be referring this as resonant frequency. Frequency is never resonant, but it's the resonance frequency. That is the frequency at resonance. The circuit may be resonant, but the frequency will not be resonant. So you always be using the terminology resonance frequency rather than resonant frequency that you would need in some of the literature you'll be reading. So we can illustrate this as follows. That the real part of the dielectric constant will have almost that kind of relationship where it picks up a little bit and then comes down. This looks like a low pass filter, so to speak. For the imaginary part, it has the peak value at the resonance frequency omega p, and it picks up and then goes down as the particles now become unable to follow the field. So the resonance frequency for electronic polarization is usually in the region, in the spectral region of the UV range, that is ultraviolet range, for most dielectric materials. The other types of polarization will exhibit qualitatively similar effects, but omega p will lie at much lower frequencies because we are dealing with much bigger or much more massive particles. Now, this for electronic polarization, the electron is usually very, very light. Now, if you are dealing with orientation or ionic polarization, okay, you will be dealing with a heavier molecule as you try to orient them within the material. So the omega p, which we saw was proportional to this, inversely proportional to the mass of the particle, then omega p will be smaller for heavier particles, so to speak. So this is a qualitative displays a presentation of the polarizability frequency responses, where we have the space charge, okay, that is the accumulation of charges at grain boundaries and the likes. Then we have the displacement, or the dipole moment, kind of polarization, and then we have the ionic, and we have the electronic around there coming to the UV light. And the epsilon double prime, that is the loss, the loss component, will also have that kind of thing. We see that it's always doing that. Of course, the resonance peaks are not going to be sharp because of the different time constants that we have in the changes. So the resonance frequencies are associated with the effective mass of the particles that are responsible for the different polarizations. And hence, the increasingly higher resonance frequencies as particle mass decreases. And now, and with that, we come to the end of the electric polarization. Now, what I want to look at is magnetic polarization, because we know that in some cases, especially when, for those of us who will be taking microwave engineering in fifth year, we'll deal with ferromagnetics and so forth. And we need to see how the magnetic polarization comes about. Strictly speaking, magnetic properties of materials are better handled using quantum mechanics. But here we are just going to use kind of some quasi-classical approach so that we don't start having to remember Schrödinger's equation. Okay? So what we can say that we can always use quantum theory of matter to explain this. And the Bose model will usually view the atom as a positive nucleus with electrons that are orbiting the nucleus at various discrete and stable radii from it. So electron motion around the nucleus may then be viewed as a microscopic current loop. So when we have a current loop will always induce a magnetic moment of magnitude that is equal to the product of that current that is flowing in the loop and multiplied by the area of that loop. And the magnetic moment will be in the direction that is normal to the area of the loop, and is therefore given by the right-hand rule. So an atom may hence be associated with a property of magnetic moment m, okay? But in reality, the magnetic moment will consist of the moment due to the electron motion in their orbits and swell as their spin. You know that we can have spin up or spin down electrons. So some atoms will possess permanent magnetic moments, while others may have moments that are induced by an applied magnetic field. So the origin of the effects will be best explained through quantum mechanics or quantum mechanics, but we are not going to go into that for now. So when we apply the magnetic field to the atom that has a permanent magnetic moment, then there will be an interaction between the magnetic field of the atom and that of the applied field, and therefore this will result in a torque that will be established that will tend to rotate the atom about an axis as it tries to align with the applied field. So suppose the atom can be represented by a current loop. Then the atom will orient itself in such a direction that its magnetic field will add to that of the external field. So such atoms will be then said to be paramagnetic. In a general way, the effect is very weak, but it's quite strong in magnetic materials or ferromagnetic materials such as iron, nickel, cobalt. Manganese is really not a magnetic material, but it just behaves the same, and gadolinium, etc. All these materials can be seen to be materials with the d shells that are not full. That is, we have partial spins in these atoms, with manganese having 5 electrons in the 3d shell and so forth. So some atoms may have no permanent magnetic moments, but induced moments will develop under the influence of an applied electric field. So the induced magnetic dipoles will orient themselves in a direction that tends to minimize the total field. That is, they'll try to be in opposition to the applied field. And the materials or the atoms with such kind of properties will then be described as diamagnetic. So whatever the mechanism of the dipole formation, whether permanent or induced, we can always assign a dipole moment M to any given atom M. So if we multiply M by the atom density N, then will give us a value of magnetic moment volume density, which we shall just describe as magnetization and give it a symbol capital M in that material. So when we have low level fields, the magnetization will be proportional to the applied magnetic intensity, H, okay, in virtually all materials, except in ferromagnetic materials, which we shall see why. So magnetization can thus be expressed in the form M equal to chi M multiplied by the magnetic intensity, field intensity H, and chi M is now just analogous to that of the electric fields. We'll call it the magnetic susceptibility for the material. So in paramagnetic materials, where the induced dipoles are tending to increase or to augment the applied field, the chi M is positive. Okay, the chi M is negative when the material is diamagnetic, because we saw that in diamagnetic materials, the induced dipoles are oriented in the direction that tries to reduce the externally applied field. So we can, similar to the electric, the polarized dielectric, we can also replace a magnetized material with equivalent volume and surface currents. Okay, this can then be modeled as infinitesimal current loops or magnetic dipoles. So consider a small current loop of moment M given by Z cap M. That is, we are assuming that the current loop has a magnetic moment oriented in the Z direction, and it's centered at the origin of a Cartesian coordinate system that is lying in the XY plane. This moment produces a magnetic vector potential A at a field point R away from the dipole, given by A, given by mu by 4 epsilon, given by the cross product between the magnetic dipole and the unit vector in the direction of the field vector by R squared, which we can interchange that and get that using the value of the integral. That is the gradient of that is, we are replacing R squared by the gradient of the 1 over R. Okay, that is 1 over R squared can always be replaced by that value there. This you can always prove for yourself when we after this. So this expression is valid for any orientation of the dipole moment and may be generalized to any location R prime of the dipole as follows: that AR, due to a dipole that is at R prime with respect to the Cartesian, to the origin at the field point, will be given by that expression there, where we are using the R we used before now by just the modulus, or the big R that we used for the electric dipole moment. And this is equal to that value there. So for a large number of dipoles that are contained in a volume V prime, bounded by a surface S prime surrounding the dipoles, the magnetic moment in an element of volume dV is therefore going to be given by the magnetization or the magnetic dipole density multiplied by the volume we are dealing with. And hence, the magnetic potential at R prime, at R, due to the entire assembly of dipoles, is therefore going to be the volume integral of that value over the of the A over the volume itself. And when we invoke Stokes' theorem, we can express this in the form that the integral of that, okay, where we are using the del operator at the source cross M minus that there. In other words, we have a value of that nature, where we have used Stokes' theorem to convert this equation into that equation, which is a surface. Okay, this term is changed into a surface integral over the whatever the surface surrounding or containing the dipole moments. So when we compare this with the magnetic potential that arises from free charge current distribution J, the volume distribution due to magnetization is then equal to or equivalent to a surface current density J, ms, equal to M cross the unit vector, outward unit vector. And the volume current density is going to be given by J of M equal to the current there, where we are using magnetic current. That's why I'm using a subscript M. This is not the actual current, electric current, but magnetic current, so to speak. So this will be the value of the equation there. So in the interior of the material, there will be incomplete cancellation of adjacent loops leading to a net volume current density. At the surface, the currents are not cancelled, and this gives rise to the equivalent current, surface current density. And therefore, in the interior of the magnetically polarized material, the magnetic field will be related to the polarization current density through Ampere's circuital law. Thus, in the absence of currents due to free charge transport, then we know that the curl of the magnetic field intensity must be equal to the current density, okay? The current density of the material. And this is going to be given by that value there, the curl of M. This is Ampere's law, so to speak, using the due to magnetization current. Or in other words, we can put all this under the same bracket, and we see that that is going to be equal to 0, which tells us that is a gradient current. It's like something which is divergent, so to speak. So we define a vector which we will call H as B divided by mu naught minus M. So this would be the field intensity with the material in place, and this is the magnetic field intensity that would occur in that area or that volume if the material was not there, and we can see that it's going to be less the magnetization of the material itself. And this gives us a value of B equal to mu naught into H plus M. And this is why we have that kind of equation. Okay. So hence, the curl of H is going to be equal to 0. Now, H is therefore called the magnetic field intensity, and in the presence of non-polarization current density J, okay, where J is actually movement of electric charge carriers, okay, then we can see that the Ampere's law will give us that equation there. One may ask us, why don't we have the plus d dt of d? It's because we are dealing right now with a magnetostatic kind of situation where we don't have time dependence. And this is what would be the case for a conductor, so to speak. So we recall that the magnetization is proportional to the magnetic field intensity under low level excitation. And therefore, we can write that B is equal to that. And if we replace that with the value of M that we saw before, we said it was just going to be expressed as chi M multiplied by H, we get mu naught into 1 plus chi M multiplied by the magnetic field intensity. And this gives us a value. Okay, we can use a relative permeability for the material mu r and multiply it by the permeability for free space. And the equivalent magnetic polarization surface current density will establish the boundary conditions on the tangential fields. So, suppose we look at a magnetic material which has that kind of value. That is, we have the flux density outside the material, flux density inside the material, and magnetization inside the material and outside the material. And we therefore have a surface current density JMS around the surface. So if we assume no currents exist due to free charge motion, that is J is equal to 0, then we can have that B naught by B outside the material, and the intensity inside the material is just going to be equal to the surface current density. And therefore, if we put these values as shown there, this must be equal to 0, or in other words, the magnetic field intensity is continuous across the boundary. That is the tangential component, so to speak. This means that the tangential component of the magnetic field intensity is continuous across a boundary between two media in the absence of free charge surface currents. Now, remember, the way we can suppress the conduction current is by using materials that are made of, magnetic materials that are made of oxides of iron or nickel and so forth, and this usually will be referred to as ferrites. So the dielectric, they have very high permeabilities, okay, but they behave as insulators, and these are usually important, especially in microwave circuits. So that brings us to the end of that particular topic. And I have only a single minute to go. So if we have any questions for dielectrics, then we can break for the Christmas break. So any question before we leave?
Yes, before we leave, the recordings, could you please upload them? The recent ones weren't uploaded.
Yeah, but you have the slides. You want my voice?
Yes.
Well, okay, I'll try to see whether, it's been giving me limits as to how many I can share.
Oh.
But I'll try to see how I can try to upload them over time.
Oh, okay.
I haven't uploaded for some time, isn't it?
Yes.
Yeah, because what I'm using, I can't put them in the drive, but
Yes.
I can send them to you from after it downloads.
Okay.
Yes. I think that's what I'll do. So you need the recordings from when we started, or what?
Yeah, I think it's the last 5 or 6 that haven't been sent.
Yeah, okay. And then I'll try to see what I can do. So any other issue?
Yes, regarding the CAT, have you set a date for it?
We said that you'll be coming for is it 2 weeks of whatever? of labs.
Yes.
So what they are using is that the last Thursday and Friday
Yes.
have been set aside for CAT.
Okay. In order to maybe easen the load for us, would it be possible to schedule it on that Friday 25th?
Friday 25th.
Yeah, on the 25th, Friday. Oh, sorry, not 25th, 18th. Friday 18th.
The last one, the time we've been given.
Yes, yes, on the last Friday.
Yeah, that's okay.
Okay, thank you.
So I'll write that down. Friday 18th.
Okay, thank you.
Okay, fine. So any other issue? So since we don't have any more issues, then I'll thank you for the attendance. Today we had a very small class. I don't know whether most of you have already traveled for Christmas. So anyway, do have a nice day. We'll meet tomorrow.
Thank you.